So my presentation will be overcoming the barriers in underwater mobile networks, and I will introduce our low power solutions and the challenges, opportunities, and also share our field experiment insights. So the presentation will include 3 parts. In the first part, I will introduce the background of underwater mobile networks, including the existing solutions and the remaining challenges. And in the second part, I will introduce our solution called underwater acoustic reconfigurable intelligent surface, which is a low power solution to overcome those current challenges. And at last, I will share some insights from our field experiments. So to begin with, why underwater mobile network is so important. So here, the bottom figure shows an invasion of the future visions for autonomous ocean observation. And it is a very important vision that it will enable the autonomous operation of the ocean monitoring system. And in this vision, there is a central part will be the underwater mobile networks, because it enables the AUV to communicate with surface facilities, for example, the surface buoys, surface vehicles, for efficient data exchanges and operation coordination. And it also enables the AUV to AUV communication, especially like when we want to perform a large swarm of AUV to perform the collaborative missions, for example, surveying, exploring a large area and mapping those ocean environment. And that will require AUV to AUV high data rate and long-range communication. The underwater mobile network will also connect AUV to the seabed-mounted sensors as shown in this figure. And the seabed-mounted sensors are also very important because we expect them to be low cost, and we can deploy them in large scale in long term to operate in the oceans for long-term underwater monitoring. And we'd like the AUVs to be able to efficiently collect the data from those large area seabed-mounted sensors and for the long-term underwater monitoring. And we can see that despite the promising vision of underwater mobile networks and how it is important in underwater the future autonomous ocean observation problem, but underwater mobile network face many research challenges. So those challenges including there is a trade-off between the communication range and the data rate. So basically, the high rate communication is very important, especially in the future. You can imagine that like when we have like AUVs to work together, we want them to be able to share the high resolution images, videos among them for the ocean exploration. And imagine in the future, the AI is also going to play more important. And for AI applications, it requires large amount of data exchanges. So all those applications require us to be able to exchange data in the high rate and long range, because we cannot expect AUVs to be very closely operating together in a large ocean. And however, making the communication long range and high rate is very difficult because there is a trade-off. If we want to push to a longer range, we will expect to have a lower data rate and vice versa. So basically, achieving the underwater communication in long range, high rate together is very challenging. And the second challenge comes from the low power requirement, especially for those seabed-mounted devices. And those devices have a very limited power supply. That means we will require to have a very to be able to communicate with AUV in ultra energy efficient way. So that means, however, due to those low power requirement, the communication range for those seabed mounted sensors will be very, very limited, typically only a few meters. So which won't be sufficient for AUV to collect the data from them in current solution. So that means we need to extend the current communication range from several meters to at least, for example, 100 meters. So that is another challenge. And the third challenge comes from the difficulty in the AUV localization, because everyone know our ocean is a GPS-denied environment. So on land, we can use GPS for precise localization in real time. That is very important, especially in autonomous driving. But in the underwater environment, our AUV also need to autonomously drive. And we don't have an existing localization infrastructure and solution yet. So, next I will introduce those three challenges one by one in details. The first one is related to the high rate underwater communication. The current solution, mainly including two. So the first one is optical communication. So for optical communication, it is capable of a very high rate communication in terms of gigabits per second. So that is good enough for high resolution image video data, but the limitation is it is highly dependent on the water clarity and turbidity. So basically for clear water, we can expect to have a communication range up to 100 meters, but in the turbid water, the range will reduce to several meters. So that means it will restrict the practical communication, the application of optical communication in a lot of real application scenarios. And we can increase the communication range using directional or laser-like optical communication. But the difficulty is with that, we need to precisely adjust the transmitter and the receiver for the directional optical communication. So that is very challenging, especially for AUVs, because we know AUVs are mobile. So they are moving all other way, and directing the AUV to AUVs precisely is very difficult. So means optical communication will be very challenging to use in the AUV mobile network. And an alternative solution is high frequency acoustic communication. When we increase the frequency of acoustic signal into 100 kilohertz to 200 kilohertz, we can achieve data rate about 100 kilobps. So although that is not very high, we can support low resolution image data transfer. So the acoustic communication can offer moderate data rate and communication range. The benefit especially compared with the optical, is acoustic signal can propagate much further away than the optical signal in water. So that's why that is one more commonly used solution for high data rate acoustic communication. So however, the high frequency acoustic signal suffer from high propagation loss, and higher frequency will increase the propagation loss in water. And for example, if we consider one existing solution which can support 100 kilobps MIMO system that can communicate with a range of 1 kilometer, in freshwater, that communication range can reduce to probably 200 meters in saltwater. The reason is because acoustic signal also have more propagation losses in salt water. That is due to the nature of the signal and the communication medium. So we can see that with the existing two solutions, actually we don't have a very practical or like a ready communication solution for the high rate, long range communication because of those very limited communication range. And it will call for new communication technology to achieve, to tackle these challenges. The second challenge related to the low power seabed mounted systems as shown in this example. So it is very challenging to provide a power supply for those devices, especially in the ocean environment. So there are some existing solutions. For example, we can use the battery power. However, we know battery has a limited lifespan. That means like when it is drawn out of battery, we either need to recharge the battery or replace it periodically. So we know that those will be very time-consuming, labor-intensive, and also expensive. And besides the battery power, we can also tether those devices into onto a surface buoy, where we can have a solar power that sustainably available for a long time. But it also has its own limitation. So the surface attachment and also the cables are vulnerable to a lot of issues. For example, the current, the severe weather, and the marine animal interferences. And so that means install those cables and maintaining the cable is also very expensive and also time consuming. So those two are very all very expensive and time-consuming, and we have a third solution that is using the energy harvesting. Basically, we can attach some energy harvester onto those seabed-mounted sensors that can harvest energy from the environment. For example, from the current, from the vibration, and the good part is it provides a sustainable power source, and also because there is no cable, tethering, no surface attachment, so it is more resilient to some weather conditions or marine life interference. But the limitation is a sustainable power source. It can only provide a very limited power supply to the system. So that means with those very limited power supply, it has to use ultra energy efficient communication solution, for example, the backscatter communication, which is a passive communication solution. And with this backscatter communication, the communication range is only a few meters. So that is true, that is only a few meters. So basically, with those a few meters and communication range, it won't be available for the current AUV to collect data from those devices. So our second challenge will be how can we extend this communication range of the backscatter communication into, for example, tens of meters or 100 meters. And the third challenge comes from the localization. And in underwater environment, we still don't have a good solution for localization yet. And there are two commonly used localization solutions, and however, both of them have their own limitations. So the first one is called the long baseline localization, short for LBL. It requires deploy of multiple reference nodes scattered in the environment, basically spacing hundreds to thousands of meters in order to achieve accurate localization. Basically, the larger the space and the higher the accuracy. But you can imagine larger spacing will increase the localization cost. And this localization solution is also very complex, also very expensive because it relies on how many transponders you can deploy. And remember, all those devices, you need to power them because they need to be deployed on the seabed, and you also need to provide power to them, typically including cable and surface buoy to provide power for those devices. And another limitation of this is it is limited to the predefined area, basically within the coverage of those reference nodes. So if you have AUV that operate in an area that don't have pre-deployed transponders, and we won't have GPS, we won't have a localization service with this. So another alternative option is using ultra-short baseline localization. So it uses an array of transceivers carried by a surface vehicle, basically a vehicle carrying mobile reference nodes. And based on compared to the LBL, the deployment of this is more flexible, and because it can be carried by the surface vehicle. And when we change our AUV missions, we can also command our surface vehicle to move with our AUV to provide continuous localization support. But the big limitation is it requires surface support. So without a surface vehicle, we won't have a localization service to the AUVs. And also, it is also very expensive because the surface vehicle are very expensive. So for example, if you have a AUV swarm, you probably will need multiple surface vehicles for that mission. So neither of those current solutions for the localization are scalable, and neither of them are low cost. And so the third challenge comes from we want to develop a low cost, scalable, and accurate localization method. So to summarize, envision those three challenges. Challenge one, how can we achieve high rate, long range together for in support the future underwater mobile networks for the video, image data transmission, and AI applications. And challenge two, how can we extend the communication range for underwater backscatter communication so that we can enable AUV to autonomously collect the sensors using an energy efficient way. And third challenge, how to develop a low cost and scalable, accurate localization method. So envision those three challenges. We have been thinking, can we develop a single solution that can address all those three challenges? Well, luckily, after some careful consideration and exploration, we found it is doable, and our proposed solution is called Underwater Acoustic Reconfigurable Intelligent Surface, short for UARIS. And I will use RIS to refer to those solutions in this presentation. So what the RIS do is it can reflect the sound waves and also create a focused reflection of the sound wave. So, so in this case, for example, if here this is the direction of our transmitter and this is the direction of our receiver, this smart surface, it can reflect and focus the sound wave to the receiver to enhance the signal power of the receiver. So in this case, we can extend the communication range of between the sender and the receiver. So it is called reconfigurable is because we can reconfigure those features of those reflectors. So each dot is one reflector, and this is a 2D array of the reflectors, and we can configure them to change the direction. So because in our real applications, we may have different receivers and moving receivers, so that means we need to be able to change the direction of our reflected wave. So that's why it's called reconfigurable and intelligent. So the benefit of this RIS is it can extend the communication range at high data rate. Basically, it doesn't require transmitter receiver to enhance their system. So we can use this RIS as some like infrastructure support to make the current transmitter and the receiver to achieve a longer communication range at the existing data rate. And another benefit is it reduces the energy requirement because it doesn't require the transmitter to increase its transmission power to reach a longer distance, because that is what currently the current strategy. If you want to reach a node further away, you need to use a higher power. It's similar to our cell phone, Wi-Fi, like it will adjust the transmission power based on the distance. So it is also used in the underwater environment. But with the RIS, we don't need to increase the transmission power, but by utilizing the RIS to focus the reflected signal to enhance the communication. And also it can serve as localization infrastructure, and by the steering information can naturally be obtained on the RIS. Basically, we can get the localization, the direction information of the transmitter to localize the transmitter. So with those envisioned those benefits of the RIS system, we also identified the design challenges. So in the radio environment, the RIS has already been widely investigated and attracted many research interest from the academia and the industry because the potential that it can enhance the communication capacity of the current radio communication systems. So however, due to the essential difference between radio waves and acoustic waves, the radio RIS cannot be directly applied to underwater acoustic RIS. So the most important reason is due to the high dynamics of the impedance of acoustic reflector. So because the most essential part of the RIS is to tune the impedance of the reflector to change the direction or change the reflected signal. So in the radio RIS, it uses a variator diode for impedance tuning. So with this, it can achieve nanohenries for inductors and picofarads for the capacitors. So that is sufficient for the radio RIS. However, in our underwater, the acoustic reflectors, it requires millihenries for inductor and nanofarads for capacitor. So if we compare those four values, we notice that what can be achieved in the radio RIS is 1,000 times lower than what we want in underwater RIS. So that means we cannot use the existing radio RIS directly in our underwater RIS. So there are also other challenges that are unique in the underwater RIS. One is the high dynamic range of the signal intensity. That is what we identified during our experiment, because for acoustic signal, it can, for example, it can travel like 1 1,000 kilometer, right? So that means if you imagine, if you have the one reflector that is 100 meter away, and there is another reflector that is 1,000 meters away. So those two reflectors should impact very severe difference in the signal strength received. So that means our smart surface needed to be robust to be able to operate in that very different operation condition. Basically, it should be work for high power and also work for low power, because we cannot control where our AUV is. It could be very close to our smart surface. It could also be very further away from our surface. Or we need to have our RIS to be able to robustly operate in all those different situations. So that this will challenge the control system design in our RIS. And in underwater RIS, it also have a more severe limitation in the power supply, because on land or radio RIS have a very unlimited power supply from power grid, from solar, but in oceans and we have a very limited power. So we will also need to have a low power limitation in the consideration in the design. So here shows an our prototype of RIS, and in this figure you can see it include a reflector array, and here is the reflector array that we made. And second, the most important part is the load impedance control network, which is the PCB board that is to control the impedance so that we can manipulate the direction of the reflected signal. And we also have a low power MCU to do the controlling and operation. So it's a low power device. So in this design, we needed to manipulate the reflected acoustic signal through precise load impedance control. So due to time limitation, I won't cover the details of the design in the RIS architecture. So if you are interested, you can look at our paper that is submitted to the archive, which now is available online. So in order to validate whether our UARS work, and we did some experiments. So for the water tank evaluation, our primary goal is to test whether our reflector work as we intended, right? We want to be able to precisely control the reflected signal of those reflectors. So in our water tank evaluation, we focus on reflector scale. Basically, we change the impedance of the single reflector and see whether it is able to manipulate the reflected signal as intended. For example, if we wanted to have a strong reflected signal, and whether we can achieve that. And when we wanted to compress the reflected signal, can we do that? So in this experiment, we change, for example, for each reflector, we change their impedance scales and observe what we measured at the receiver side. So here, this waveform is the received signal measured at the receiver, and you can see those are the stages or the scales of our impedance, and you can see we can manipulate the received signal, because the received signal is a combination of the direct signal, basically the signal from transmitter to the receiver, and also the reflected signal from the reflector to the receiver. So you can see the direct signal is constant, right? Because the transmitter doesn't change the signal. So when we change the reflector's impedance, the changing part is the signal strength of the reflected signal. So basically, the received signal shows the combination or supercomposition of the direct signal and reflected signal. Basically, the signal amplitude variance actually is the reflected signal variation. So you can see we are able to precisely manipulate the signal strength of the reflected signal and on the single reflector scale. So this will be the foundation of our UARS because we require precise control of each reflector in order to code, in order to be able to control the whole array so that it can form a directionality as we intended. So in our lake test, we scale up the validation into the array scale. Basically, we wanted to test the whole system. And this test, it includes the whole 6x4 reflector array. And we adjusted the load impedance of all those reflectors. And we would like to see whether we can change the direction of our reflected signal, right? Because that is our ultimate goal. So if we can change the direction of our reflected signal, that means we can enhance the signal strength at the receiver, and so that we can enhance the communication range between the transmitter and the receiver. So in order to achieve this specifically, what we did is change the impedance of all 24 reflectors. So when the impedance of all 24 reflectors are identical, the directionality will be 90 degrees to the reflector surface. So that direction aligns with the receiver's direction. So basically, that 90 degree indicate that the reflected signal should direct to the receiver's direction. So with that, we should expect to observe significant reflected signal, right? Because that should be because our surface is directing the reflected signal towards the receiver. So in the bottom figure, we shows the result of the, that is actually only the amplitude of the received signal. So as we mentioned, the received signal include both the direct signal from the transmitter and also the reflected signal from the surface, basically the RIS. So basically this is actually the direct signal from the transmitter, and the steps shows the reflected signal because we wanted to separate the reflected signal. So what we did is we turn the reflector surface on and off and see what's the difference. So if, for example, the reflector is not working, so we should not see any difference, right? And so when we switch it on and off, we actually can see that in this blue curve, we can see obvious reflected signal. And but we can it is not sufficient enough because we cannot we are not sure, for example, whether this directionality manipulation is working at all, right? So with this, we only tested, okay, our reflector is working, but I'm not sure whether it is through this direction or is broadcasting, right? So what we did is we changed the direction. So from 90 degree to the receiver to a different direction. So when we deviate the direction away from the receiver, we should expect a reduced reflection signal. So that is the result of the 60 degree and 45 degree. That means 30 degree away from the receiver and 45 degree away from the receiver. So we can see, again, so we needed to look at those steps. So you can see that by changing those directions, we are able to reduce the reflected signal. You can see those reflected signal become less observable, and in this case, like even the reflected signal disappear. So basically, it's not making any impacts because we moved the direction of the reflected signal away so that this receiver is not receiving the reflected signal. So with this lake test, although not very comprehensive, but we validated that the system is working, and we are able to enhance the signal strength by using this RIS, and then extend the communication range for the underwater communications, because with the enhanced signal strength, we are able to communicate further away. So that is the first application of UARS. And then our second, because our second challenge is whether we can extend the communication range of the backscattered communication. So the traditional backscattered communication has a very similar architecture to the RIS. So that's why we can use the RIS structure to enhance the backscatter communication. So traditional backscatter communication just use a single reflector. So by change the load of the reflector, basically using a switch on and off, we can manipulate the backscattered or reflected signal, and this signal strength variation will carry 0 and 1 bits, so that we can send 0, 1 bits to the receiver. So because the backscatter signal, this backscatter communication, it only uses one single reflector, so the backscattered signal strength is very limited. And so that's the reason why it can only communicate with like a few meters, like a communication range. So we can naturally expect to have directional backscatter communication with this RIS architecture. Basically, instead of have a single reflector, we can have an array of this reflector, and we can use control method to change the directionality of this backscattered communication. And with this beamforming gun, we can extend the communication range. And what promising is this beamforming gun, it scales linearly with the number of reflectors. Basically, if, for example, one reflector is too small, is too weak, you can use 4. And if 4 is not a big, significant enough, you can use 20. Basically, you can use a larger array to achieve a higher gain and increasing your communication range. And also, because it still work passively, and it has a very low power in the order of macro watts. So that means it is practical for the seabed mounted sensors. So with this UARS, we can enhance the communication range of the backscatter system. So to summarize, we can see that RIS can provide a solution to enhance the communication range in high rate communication, and it enhance the communication range for backscatter communication. So this enhancement is very straightforward. And then we come to our third challenge, which is the localization. So we can see that the RIS for localization is not that straightforward, and that means there are a lot of challenges in order to make it to use it for localization. So, but we know the benefit of RIS is the low power. Basically, for the transponders, we want it to work for a longer time, and that low power is a good benefit. And also, we wanted to extend the operational range because our RS provide the directional gain, and we have a good communication range, but it also has its own limitations. So before introducing the limitation of RIS, let's take a look at a traditional localization. Basically, in the traditional localization, we leverage the position of those three reference nodes. So basically, we know the position of those three reference nodes. And if we know the distance between AUV to those three nodes, we can use triangulation to calculate the 3D positioning of this AUV. So that is the principle of localization. And what the traditional localization do is let the AUV to send out a ping signal, basically a very short signal to those transponders, and the transponder will reply immediately so that the AUV can measure the round trip time between sending out the ping and receiving the echo. So by measuring this round trip time, we can get the single time of flight, and based on the time of flight, we can get the range or the distance by multiplying the propagation speed of acoustic signal, which is a predefined speed. So that is the traditional localization. So the reason why it is working is because those traditional transponders works actively. Basically, there is no there is no delay between receiving the ping and replying the echo. However, it won't be the case for the passive system. So because in order to conserve energy, the system will stay in the off state. Basically, it needed to in deep sleep mode or completely off in order to save energy for the RIS. And that means when the ping reach the transponder, it will take some time to wake up the device. So you can imagine when the signal arrives, so it will charge a small capacitor. So only when it reaches voltage level, it will wake up the transponder. So that charging time is not negligible in the real situation. So we call that charging time as wake-up delay. So with that, the round trip time will be the time of flight in the downlink, and the wake-up delay on the transponder, and then the uplink time of flight. So that means in order to get the time of flight, we have to get an accurate estimation to the wake-up delay. So unfortunately, this delay is not deterministic because it is relying on the distance. Basically, if you have a closer transponder, that the signal, the ping signal it receives is strong, so it will wake up very quickly. But for a long-distance transponder, the signal it receives is weaker, so that means it will accumulate longer time in order to wake up the device. So that means this wake-up time is not fixed, but depending on the distance. So you can see that with the significant wake-up delay uncertainty, and we have to come up one solution that able to measure the wake-up time. So luckily, we are able to measure the wake-up time in very accurately. So for example, here we can achieve like 20 to 80 microsecond error, and with the wake-up time, we can get the TOF and use the trilateralization to localize the AUV. So that means we indeed can use RIS as a cost-efficient localization method for AUV network. So to summarize, we now have a solution which is low power and cost efficient that can assist the high rate long range AUV to AUV communication, can do the directional backscatter communication for AUV to the seabed mounted system, and also we can use the AUV as to provide the localization infrastructure for the future AUV localization. So far we have done the proof of concept validation, and we verified the hardware, the control in lake tank test and also lake test. So however, there are a lot of unanswered questions. So for example, we'd like to know what are the performance gap between the experimental and the theoretical results. So it's very easy to estimate what's the theoretical performance, but we all know that we cannot achieve that theoretical performance. But how well our experiment can do, we don't know yet. And also how significant is the quantitative improvement in the communication range. So our current experiment is only 21 meter, which is not sufficient for the larger scale validation of the communication range, because the 21 meter is so close that we don't need RIS for the communication range enhancement. And also, how accurate is the RIS in controlling the direction? So now we only know we can change the direction from one direction to another, but how accurate it is, we don't know. So in order to do that, like we need to deploy like the probes in same distance to the transmitter and not uniformly spacing in degree. So that will require, but right now we only have one measuring probe, and that will require at least 10 probes in precise deployment, which is not that will require a lot of resources. And so for future work, we wanted to further enhance the architecture of the RIS and use it for higher frequency, for higher data rate, and provide a quantitative evaluation with larger scale simulation, larger scale experiment if possible, and also tailor the network protocol design for the RIS assisted networking. So I can quickly go through some experiment insights. So first is the performance gap. Basically, everyone know that the performance of theoretical and experiment are large. And we also noticed that the theoretical and the simulation results are also large. So we did a console simulation in ideal condition, basically no hardware imperfection, no hardware inconsistency. Even this ideal condition, we can still observe the direction deviate from 45 to 35 degrees. And also there are some lobes missing, and also there is a lobe apparent in a different direction. So basically, we can expect a huger gap between theoretical and experimental. And also the experiment is very, very expensive and lengthy. So for example, I attended 3 C experiments. So each experiment will take 1 to 2 years preparation. And also like when for a 1 day long, 1 week long sea experiment, we usually only get 1 to 2 days like meaningful results. So basically all the remaining days, like we won't get any meaningful results. And also the results are unexpected, and basically the good part is it can generate new findings. And so we had those publications from those experiments, and also my dissertation was focusing on investigating those real system features and understand the impacts in the underwater networking. But the limitation is it won't be meaningful for network performance, because for network performance validation, we want to have an ideal configuration, basically. But in the reality, it won't be like, it will be very dynamic and won't be as we expected.